All right, and we're back. So I have just a couple more slides to talk through for limits. Okay, just a couple more slides to talk through. Shall we get started so you can have work day? Good. Just so you guys know, we're not going to quiz until section like 2-4. So we got a while till our next quiz. Okay. Alrighty. So we did this. We talked about heavy side function. We talked about left hand, right hand limits. And then we started talking about this idea where if you input values of x, the smaller the closer to 0 I make my values, the bigger it's going to get. And we were talking about these ideas of infinite limits, as if I take x closer and closer to a, so in this case x going closer and closer to 0, the value of the function gets infinitely bigger. It doesn't converge to one number, but it gets infinitely bigger, as big as it possibly can get. Okay? And that is the idea of an infinite limit. And we talked right at the end about vertical asymptotes, right? That was where we stopped, correct? Yeah. We talked about vertical asymptote. Guys, honestly, I wish I could teach the idea of a limit when you learn the idea of a vertical asymptote, because they go hand in hand. Okay? The idea of a limit, as I take x to get closer and closer to some number, it's either going to get really big or really small. That is a vertical asymptote. Because how I explain a vertical asymptote to you in algebra 2 is just that, I'm going to get closer and closer to the number, but I'm never going to reach it, right? And it's just going to go up, right? And that's kind of like a really basic definition of it. But this is the more eloquent way to say it. The limit, as x gets closer and closer to some value a, is going to be equal to infinity, right? It's going to be equal to infinity, but not just, or negative infinity, right? It's either going to dive up or dive down. However, the limit may still not exist at a vertical asymptote. Let me show you something like this. If I've got some vertical asymptote here, and I go here and there, okay? At that a value, does the limit exist? No, it does not exist, and here's why. If I think about it coming from the left side, what's the limit as x approaches a from the left? Negative infinity, because it's going to dive down. What's the limit as x approaches a from the right? Positive infinity. So therefore, the full limit does not exist. Does that mean there's no asymptote there? No. That just means that the limit as x approaches a negative was negative infinity. This is this one here. And the limit as x approaches a positive is positive infinity. It's okay that the limits don't match up. That just means that the full limit does not exist, but it doesn't matter for vertical asymptotes. Just one of those things has to be true. Okay, at least one of those statements must be true. All right, let's find the limit as x approaches 3 from 2x from the positive of 2x over x minus 3. The limit as x approaches 3 negative of 2x x minus 3. Now, from our algebraic rules, like on the last test, where is the vertical asymptote? Where is the vertical asymptote of any rational function where the denominator equals 0, right? Where the denominator equals 0 is a vertical asymptote, unless it had been canceled out, which would make a whole. But the denominator of any rational function is a vertical asymptote. Do we know how the function is going to behave around it? No, we don't know that. Like if I were to ask you to graph this, 2x over x minus 3, the best thing that you could possibly do is to just kind of like plug and chug and run numbers. That's actually what we're going to do here as well. We're going to do that exact same thing, just to see how it behaves at 3. Like if I go to graph this, I'm going to see here something at 3. Do I know it's going to dive up at 3 on the left, or down at 3 on the left, or up at 3 on the right, or down? I don't know yet. Let's see what happens. Okay, so I'm going to pick a value really close to 3 on the left side of it. Say 2.9. So we're going to say 2 times 2.9 divided by, I've got to put this in parentheses, 2.9 minus 3. okay, what can you say on the, well, I guess I should run another value, but as I look at this, looks like it's negative on the left side of the asymptote, isn't it? Right. Let's run another one just for good measure. I mean, this is something that you should do. Let's say 2.99. Let's insert a 9. Did I hit it? Oh, one. Insert a 9. Okay, yeah, that makes sense. It's going to keep getting even more negative, right? So that means I know at 3, it's going to look like this. I don't know how this is behaving. That's just a sketch. That's just a guess. But I know, perfect. As I get closer to 3, it's going to dive downward from the left side. Let's see what's happening on the right side. Do I know that they're both going to dive downward? No, I don't know that. I can't say that. Okay? And I can't say that because it could behave completely differently. So let's do 3 positive on the right side of 3. 2 times 3.1 divided by 3.1 minus 3. 62. Okay. Let's run one more number closer to 3. Let's say 3.01. Oh, one too many. 3.01. 602. Okay. So I know the closer I get to 3 on the right, the more positive it gets. Again, I don't know what's happening elsewhere. That's really for chapter 4 to figure out what's going on in other places. I guess I do know that. Can anybody tell me where the horizontal asymptote would be? Ooh, this is fun. Where would the horizontal asymptote be? 2. Yeah, 2. And the reason being is because the degrees on top and bottom match. So therefore, you take the leading coefficient off the top divided by the leading coefficient off the bottom. So I do know that there is a horizontal asymptote at 2. But that I do know that it crosses at 0, 0 because the numerator. That's okay. I'm gonna get better at this then. Here's 2. I'm gonna do a better diagram here then. Yeah, no. Maybe a little bit more. Yeah, no. Yeah, no. There we go. Oh, let's see how close I got. Hey, I did pretty good. Questions about that? So you can figure out what it's going to look like around the vertical asymptote by using the ideas of limit, by knowing, okay, it's going to keep going, getting more positive or more negative. You can kind of get an idea what it's going to look like around it. All right, find the vertical asymptotes of tangent x. Tangent x. Now, you might know where the vertical asymptotes are, right? You might know where the vertical asymptotes are just from your past experiences. But let's kind of take a look at it with the ideas of limits. Okay, so think about it this way. What is tangent really equal to? What is tangent equal to? What over what? Not opposite over adjacent. I'm talking about sine and cosine. Sine divided by cosine, right? Tangent of x is equal to sine of x divided by cosine of x. Where should vertical asymptotes arise? Where the denominator equals 0, right? The vertical asymptotes are where cosine x equal to 0. Okay, so what places would have the cosine equaling 0? Where would cosine equal 0? Right, on the circle. But be careful. What is cosine, x or what? X, right? So if I'm looking at pi, pi's over here. X is -1, so where do I want to go? Up here, right? Because here, at the axis, that's where it would be 0. So instead of pi, it's 1/2 pi, right? Pi over 2. Or 3 pi over 2, right? I don't know if I made those rotations the right way for you, but pi over 2 and 3 pi over 2. So x would be equal to pi over 2 and then 3 pi over 2. Right, those are the two locations. And I could say find the vertical asymptotes. Okay. Pi over 2 plus 2 pi n, and then 3 pi over 2 plus 2 pi n. Now that we should have been able to do already. Like that should not be really new for us here. But what I want to say is basically, let's make a conclusion about that. Let's make a conclusion, or let's make a little bit better of a statement about that. What if I say the limit as x approaches pi over 2 of tangent of x? What is the limit as x approaches pi over 2 of tangent of x? Well, I guess to truly investigate what the limit is, I need to look at the limit from both sides, don't I? Because, I don't know, maybe this might not even exist. It doesn't. So let's say the limit as x approaches pi over 2 from the negative, from the left side. Okay, now think about the unit circle. I guess I should do this on the board so we can all see it. Think about the unit circle. Okay, as I approach 90, as I get closer and closer and closer to 90, right? As I closer to 90, from going this way, right? What's happening to tangent? Anybody know what's happening to tangent? Well, I guess if you don't know what's happening to tangent, you should think about it as sine divided by cosine. Because if I think about the denominator of any fraction, if I make the denominator smaller, what happens to the whole value? Bigger, right? As I continually make the denominator of a fraction smaller, I make the whole bigger. So if tangent is sine over cosine, what's happening to cosine as I get closer and closer to the axis? What's happening to my x values as I get closer and closer to the axis? They're getting smaller, aren't they? So that means cosine is getting smaller and smaller and smaller as I get closer to my axis. That means my denominator of my fraction is getting smaller and smaller, which makes the whole value of tangent get bigger and bigger and bigger. You see what I mean? So that means the limit as x approaches pi over 2 from the left side of tangent of x is going to be equal to positive infinity. It's going to keep getting bigger and bigger and bigger. Could I run values? Like, could I just do the same old plug and chunk method as we've done before? Sure. You just got to strategically pick them. You know, think about pi over 2, think about where that is, and then have to go plug in values to the left of that value. But we know the unit circle, so let's use what we know about the unit circle. Okay, well, what is the limit as x approaches... Can't extend my screen. Okay. X approaches pi over 2 from the positive side of tangent of x. And be careful when I say positive side, I just mean the bigger side. Okay, so what happens here? What happens there? What about my x values now? They're going to keep getting bigger. It's going to make tangent keep getting bigger and bigger. However, the sign on tangent is going to be negative, isn't it? Think about all students take calculus. All students take, only sine is positive in this quadrant, right? Tangent is negative in this quadrant. So that means this is negative infinity. Okay. Now I could run that same process, but what does this tell you about the full limit as x approaches pi over 2 of tangent of x? It does not exist. Is there a vertical asymptote there still? Yeah, there is. Definitely. Okay. Definitely there is. And again, I could run that whole same process, but if we look at the graph of tangent of x, we know that it's periodic. We know that it's going to say that exact same thing. right? So, and we know the period of tangent is negative pi over 2 to pi over 2. So we know that exact same thing where it goes up on the left side, down on the right side, up on the left side, down on the right side is going to happen again at 3 pi over 2 as well. Okay. So we can use this idea and incorporate what we know about tangents as well. I just thought that was a really cool example. Last thing we have here, when we talk about natural log, this is another kind of thing to remember. The limit as x approaches 0 positive of ln of x is negative infinity. What is the limit as x approaches 0 of ln of x? What is the limit as x approaches 0? What if I take off that positive? What would you say? You would say it does not exist. And it doesn't exist because there is nothing on the left side of 0 for ln of x. If I tried to plug in a negative number for ln of x, that would not work. Any longer than when you try to plug in a negative number, it's not going to happen. Okay? So that's why we have to make this distinction where we say the limit as x goes to 0 positive of ln of x is negative infinity, which means that there's a negative vertical asymptote. When I say negative vertical asymptote, I mean it's going to dive down and only down, right, at ln of x at 0. All right, that's all we have for the notes for section 2.2. I'm going to let you work on your homework the rest of the period. Sound good? There you go.